Okay, thank you. So welcome everybody. I'm going to present a talk about attacking assumptions on image load callbacks. So it's going to be a Windows internal talk. And so who am I? Why am I qualified about talking about this? I am a security researcher. I work at Hunt Hackett, which is a cybersecurity company in the Netherlands, mostly specializing in managed detection and response. I personally do all sorts of Windows internal stuff, system programming, reverse engineering. I have social media accounts, and you might have seen me under this nickname with my contributions to NTDoc, System Informer, and PHNT header files. So the topic I'm going to cover today is a built-in Windows feature. It provides a mechanism for notifying that interested drivers, about the DLL image load events. So DLLs, dynamic load libraries, executable modules that Windows programs can load. And drivers can subscribe to these notifications. And it is generally considered as a reliable mechanism used by lots of security products because it is a very useful mechanism. There is a documented API for registering these callbacks for the drivers. And why is this topic important? Well, from the defender's perspective, it is a very natural point for inspecting loaded code, right? Somebody loads a library, and we want to log, analyze the file, and there are security products that expose this functionality. Sysmon exposes it as event 7. You can play with it quite easily. And of course, many antivirus EDR products. Another application, aside of scanning the file for viruses at this natural point of progression of loading, is to enforce custom code citing policies. So one example is a System Informer. We're going to talk about it. It uses this functionality. But of course, lots of EDRs use those kind of mechanisms for implementing custom protections, maybe on top of protected process lights, which is a built-in Windows feature, maybe outside of that. And so as attackers, we're interested in that because if we break all of the above, we succeed, right? So from the application perspective, using this functionality is very transparent. You issue a load library call. It goes into NTDLL, into the loader code, then into a system call that maps NT-map view of section. Section here refers to a memory projection object. It's a kernel term for a memory projection, right? And inside Windows kernel, there's a function that invokes these image notify routines. So we should immediately acknowledge that there is a limited scope to this functionality. We need to know what it is and what it isn't, because it is a notification about image loads, not just any executable code. And why is it important? Because we can have private memory that is executable, right? Not all of the executable code is backed by an image file. There are also different types of sections, which are data sections. They can potentially also be executable, also not covered by this functionality. And since people consider this a reliable mechanism, the image load callbacks, that's why we have all these manual mapping techniques that try to just avoid it altogether. So from the driver perspective, the registration routine is documented on Microsoft website. A driver provides a function, a system invokes it. That's as simple as that. This is the prototype for the function. The callback receives the image file name, which is really nice, the process ID, where it happens, and a structure with image information. This structure includes a bunch of different fields, such as the base address, where the image is going to be in the address space, the signing level for Microsoft binaries only, unfortunately, and a bunch of different flags. And if we look at the extended version of this structure, we also get the file object pointer, which is going to be useful later. So when it comes to the behavior, we can immediately tell, since we receive the base address, we can use this base address to read the image while the callback executes. So it's a post-operation callback. There is also no cancellation available. The callback routine is typed to return void, not an NT status, so we cannot change the return status of NT-map view of section. We can still unmap the image because we have the base address, and in the driver we can just call NT unmap view of section. But there are some compatibility issues with that, because since we cannot change the status code, the function is going to return a successful code, but then we unmap the image, so the code is probably going to crash. So that's a bit of an issue. Also, it's a synchronous callback, which is quite nice. It's going to wait until the driver completes the execution of the callback until releasing the thread that performed the operation. Unlike other asynchronous, natural asynchronous mechanisms like event tracing for Windows. And there is a pitfall. We saw that it is post-operation synchronous, which is an odd combination, because the calling thread, yes, it is getting stuck in the kernel because it's a synchronous callback. However, it's a post-operation callback, meaning the image is already mapped in the address space. So it is visible to all other threads, which is a bit of a problem if other threads can immediately access it, erasing the callback. And if we manage to find a way to prolong the callback execution, that's going to be quite useful. We can exploit it. So it's time to formalize the research questions we want to cover. Right? We want to know about the operating system mechanisms that are involved in the execution of the callback. We need to know what is the API surface, the attack surface available to us for interacting with these mechanisms, right? Because we want to somehow influence the flow and maybe try to break some things. Then we need to analyze what assumptions exist. Specifically, there are two categories. Assumptions that are relied upon in the operating system to make sure to deliver the callback and provide all the necessary information in the callback parameters. And of course, there are some assumptions on the driver side, that drivers that use the callback, they probably want to do something with the file, maybe open it, maybe hash it, scan for viruses. All of these operations can potentially fail. And we want to violate these assumptions. We need to figure out how. And of course, from the defensive perspective, then we want to try to mitigate the damage and find ways to make sure that nobody can break this functionality. So a bit of context about files and section objects, which are memory mapping objects. Mapping executable code into memory from disk is a three-step process. First of all, we need to open the file. Open file, create file, system calls that do that. They give us a handle to the file. Then we create a section object via create section. And specifically, there are several types of sections, 2 or 3 depending on how you count it. We need sec image flag, which corresponds to executable image sections. There are also data sections or page file-based sections. And then we map it, map view of section. And important parts to notice is that step 2, creating section, requires a file. There are sections you can create without a file, but if it's an image section, it needs a file. And step 3 does not require a file. It only requires a section object. So by the time we created the section object, we can close the file, we can try to mess with it, delete it, doesn't matter. As long as we keep the section object handle, we can map it. And this is a level of interaction involved, right? It makes sense from the design perspective, right? We have the I/O subsystem that deals with files, and we have the memory management subsystem that deals with section objects and mapped memory. So because there is separation, there are more points of influence we can try to abuse. And of course, more caching and opportunities for mismatch. So here's the diagram we see. There is a file on disk, what we consider on disk, so the data, the content plus some metadata, the file name, etc. Then we have the file object, which is a kernel object that corresponds to something on disk. And then we have a section object that we create that references the file object. And then we have the mapped memory that references the section object. So if somebody needs to know the name of the mapped memory, it needs to go through this chain to ask the file object about its name. So when it comes to this callback, we need to, we already want to analyze some assumptions. And there are quite a few of them. Effectively, they cover all the operations that can potentially fail upon execution, either as part of the callback delivery mechanism or as part of the driver functionality. So the assumptions are, the file still exists. We are going to discuss them in more detail later. Its name is possible to query, an operation that can potentially fail. The name is correct. Maybe some cache issues. And then after that, we are done with preparing the parameters for the callbacks. The operating system is done with it. And it gets to the driver assumptions, where the driver is probably, if the driver doesn't do anything in the callback, sure, there are no assumptions. But if the driver tries to do something useful with the file, such as scan it for viruses, well, probably need to open it, which might fail. Probably might get redirected upon opening, which is a potential issue to consider. And then the driver will try to read it and assume that what it read from the file corresponds to memory. So a few different things that can go wrong. And here's the first assumption, right? The file still exists. The idea is the following. We have greater control over the lifetime since the creation is separated into several steps. And we cannot detach the file object from the section object. It's both our kernel objects. There is a pointer between of them in the kernel space. We don't touch that. However, we can try to mess with the file on disk via file system APIs and somehow detach it from the file object. And if there is no file on disk, there is no name to report. So maybe it's going to break the driver. And here's the technique. If you try to delete a file that is currently used by, maybe it's an executable that is being run or a DLL module that is being in use, being loaded, we cannot do that. If we try to delete a file that is that has a section assigned to it, the operation phase with status cannot delete. However, it only applies if the section already exists. Before we create the section, we can mark the file for deletion. Deletion is not an operation that happens immediately upon request. It happens when we close the file. Before that, the file is only marked for deletion. So what we can do is we open the file, we mark it for deletion. We still have the file handled, even though it's about to get deleted when we close it. But before we close it, we create the section object, and then we close it. Now we have a section object, and the file got deleted because it has the flag already set. Only setting the flag is restricted upon when the sections exist. If the flag is already set, the file is going to get deleted when we close it. So by the time we execute the callback, by the time we map the file, it is already gone. There is no such file, there is no name to report, no file to open. It's similar to a process ghosting technique, so it is a somewhat known idea. Other things you can probably do here, I'm not going to cover them in the slides, but you will find them in the presentation later on, the presentation that is going to be published. You can mess with files in different ways. For instance, you have scope for files, such as transactions. Maybe you cannot delete the file, but if you roll back the entire transactions, all of the files in this transaction are going to be gone. Again, another way to destroy files before we map them, even though we still have a section object. Or maybe we just nuke the entire volume where the files are located, such as mount an ISO, create a section, unmount, and then map it. By the time of execution, the same applies. We are going to have a callback executing on a section which does not have a file associated to it, like effectively a file on disk. The second assumption we will cover is about the existence of the name. Consider restrictions that we have on file names, right? There are some special characters that we cannot use, although Windows is quite relaxed in this requirement. But still, if there is a character that is not allowed, all of the APIs are going to block it. We cannot just create files with restricted characters. And even the well-known file names like con, LPT, that we mentioned in the previous presentation, these are only abstractions on the Windows 32 user mode level. Drivers allow them, and so only some characters are the issue. We can try to bypass this restriction by patching the volume, such as creating a malformed ISO file and then mounting it. But in my experience, it just gives an error about a corrupt file or a corrupt volume. So another restriction is the length. There are some restrictions on the name of the file. What are these restrictions? What is the maximum length? Well, if you think it is 260 or max path, no, not really. It is a legacy Win32 level user mode requirement. Still, there are lots of applications that will break above this limit, but that's not really a concern for drivers. Maybe you thought the answer how long the name can be is 32,767, which is a value that appears in documentation. And the answer is yes, but also no. It's not exactly the limit. And also, why this number? Well, the reason is simple. The value comes from how Windows addresses strings when it passes them to kernel mode from user mode. There's a structure called Unicode string. It defines a buffer that with a specific length. So when we want to pass a string, we prepare this structure and then pass it to a system call. And the structure defines the length of the buffer as ushort, which is unsigned 2-byte value. So values from 0 to 65,535. But it defines the length in bytes. So considering byte characters that are 2 bytes, it's going to be exactly 32,767. This is the limit how much you can address. You cannot pass longer strings to system calls. That's it. So here's the idea. Let's try to break this assumption, because file names consist of 2 different parts, right? First of all, there is the volume name. In Win32 terms, we usually deal with like C:, which is a symbolic link to /device /hard disk volume some number. So this is the name of the volume. And then there is the path on the volume itself, such as /Windows system32. File system drivers deal with the on volume paths, only the second component. And, wouldn't you know it, NTFS allows this part to be up to the Unicode string limit. So the problem is, the full name is slightly longer. It includes both the volume and the on-volume component. So if one of them gets very close to the limit, what happens to the overall result? It will overflow. You can have files that are addressable by the file system driver if you do a relative open operation, but they do not have a full name that is possible to use to just open the file, which is quite insane. It's a file kind of without a name, with a name, but without ability to immediately open it. And the way it looks is kind of fun. If we try it on sysmon, very, very long names, trying to load it as a DLL, sysmon either fails with integer overflow, so it knows it does some checks, or reports a broken name, such as like an empty string or a single character name. And of course, then the tool fails to hash the file and collect all the metadata about it, because it cannot really open it anyway. And on the bottom, you see a screenshot from System Informer. This looks really cursed. It is a truncated part of the file name. It overflowed beyond the 65K limit and underflowed the volume name part, which looks really weird. But that's what the operating system reports. Another assumption that is very interesting is that the name reported by the image section is correct. The problem with renames in general is that these are non-owning references. If you have a file handle or a file object pointer in case of kernel code, you are using the same file no matter what. If somebody renames it, you still use the same file. If you work with strings, all of the strings become outdated the moment somebody changes something related to file names. And that's a bit of a problem, because the callback provides you with the file name, which might get outdated. So what about queries against the section object itself? Well, the answer, whether it updates or returns a cached wrong string, depends on the underlying file object, because section objects do not cache file names. They ask the underlying file object. We saw on the diagram before, there is a link between section objects and file objects. And when the section object asks the underlying file system driver, something interesting is going to happen. We can perform a simple experiment, even without sections. We open a file, we rename it, and we query the name back from the file. There is NT-query information file that can retrieve lots of information, including the file name. And if we try it on NTFS, everything works as expected. NTFS tracks renames. It doesn't matter if you do it on the same handle or open the file another time and then rename it there. It's not a problem. However, if we look at the multiple UNC provider, landman redirector, or // localhost something. It's a local SMB redirector. This is a functionality built into Windows. You can use it without networking stack pretty much. And it's a level of abstraction that fails to track renames. So if we open the file, we rename it, even on the same handle, the file still is going to report the old name, which it's also going to report to the image callback delivery mechanism. So the driver is going to receive the outdated name even though there is an updated one. So because of that, since it reports the old name, which is not occupied by the moment we rename the file, we can plant something else there. We can find a way to put another file onto the place of the original one and make the driver believe that the file being loaded is another one, which is a very useful primitive. And then there is another interesting find. A user reported a bug in x64dbg. The x64dbg failed to resolve a file reported by an image load debug event. So it's a debugger. It receives information similar to image load callbacks for the drivers, but it's a debugging mechanism. And it looks like the file that the system provided has the wrong name. Somehow, somewhere, something broke, and then the image load event reported the stale name. So the user actually accidentally discovered an attack on rename tracking. And there was a long discussion trying to figure out what it is on the System Informer/Winsiders Discord. You can check it out. So this is the attack. You can effectively discovered by a user accidentally. We cannot rename usually a parent directory of a file. The user was just moving stuff around, and what happened is that they renamed the directory that contains some executable files. Usually you cannot do that if there are handles to the files. So if something is open in a directory, you cannot rename this directory. However, the restriction does not apply to section objects. So if you have a section object but no file handles, you can rename the parent directory, and it is going to break rename tracking. So here's the attack vector based on it. You have a directory, you open a file in it, you close the file, but before that you create a section object. And then you rename the directory, and now the file object cached in the section is going to continue returning the old name, even though we already renamed the directory. And again, we can plant something under the old name, some different file. And another assumption we covered, now on the driver level. The driver will usually try to open the file in the callback, because sure, maybe there are some drivers that just log events without opening files, but that's not very interesting. Usually you want to scan it. And are there any features built into the operating system that can prevent files from opening? Well, quite a few, but some of them are only user mode concerns, such as security descriptors. Usually drivers don't have an issue with that. Even admins can bypass most of the things that non-privileged users can throw at them. There's also sharing mode. Again, there's a flag for drivers to bypass, though it's not a real attack scenario. But it still can be useful, and it also can be self-inflicted. When you open a file, you specify what parts of access mask you want to share with other callers. So a combination of file share read, file share write, and file share delete. If you don't specify a flag and there is an existing handle with this specific access, the operation is going to fail with status sharing violation. And there is actually an antivirus product that fails to scan a file if somebody has a delete handle on it, just because they decided to somehow, for some reason, they decided to open the file without the share delete. So they get a self-inflicted sharing violation, which is quite absurd, but that's what happens. And another feature that can block file opens is encrypted file system. There was a nice trick published by Jonas Luke on Twitter, where you go and encrypt in the properties the main executable of Defender. You encrypt it under your current user, and so on the next reboot, when the system user tries to start the file, start the Defender, it's going to fail because the file is encrypted under different credentials, which is fun, but maybe not exactly immediately useful here. So what is? Well, opportunistic locks. It's the favorite mechanism for winning all sorts of race conditions when it comes to file system operations. Locks can postpone file open operations until acknowledgement. So you open a file, you put an opportunistic lock on it, and then anybody who tries to open the file, so in case of batch up locks, for anything beyond read attributes, write attributes, and synchronize access, they are going to get stuck waiting for you to acknowledge the operation. It is a very powerful primitive. There are many flavors of it. They can block open, write, delete operations. But specifically for our case, open is the best option. So here is the attack. We can abuse the fact that the callback is a post-operation callback. So we already saw when the callback executes, the memory is already there. So let's say we sacrifice a thread. We perform an operation. We try to map an executable file that is currently op-locked. So there is an opportunistic lock on the file. When we try to load it, it is going to execute the callback, which will, we assume, try to open the file and get stuck for acknowledgement. So our thread is waiting for the callback, and the callback waiting for our acknowledgement. But while we postpone the operation, the memory is already mapped. We can use it for another thread. So it might be useful. Another simple way to block the file open operation is to make sure it is a file that is pending deletion. The setup is very straightforward. We open a file, we mark it for deletion. Again, as I said, deletion does not apply immediately. It applies when we close the file. And we can also cancel it. There is an nt set information file with the file disposition information info class. We can set it to true. We can set it to false. But when it is set to true, all other attempts to open the file are going to fail with status delete pending, because the file is still there. It is still visible in the file system namespace, but it is not something you can open. So the callback is going to fail. There is another assumption. We are getting to the end of it. The operation, we assume, that opens the right file, right? Or at least the driver assumes. The correct name is actually not enough. Even though the file might return the correct name under which it was opened, the name can still be, first, ambiguous, and second, it can be redirected. And there are very useful ways to redirect files, including junction points, which are available to non-administrators. So also used in quite a lot of attacks, which we can apply here. However, there is a problem. Usually when we deal with, when we want to use junction points, we supply the file name or we plant a junction point under a specific location. Here, however, we receive the file name from the system that the system queried from the file object. And all the reparsed points, such as junctions, symbolic links, they apply on the open operation, which means that by the time the system queries the name, it already followed all of the reparsed points and resolved the file name. So usually we are going to receive the full normalized name with all the intermediate points followed. And that's what happens on NTFS. However, the same multiple UNC provider, Landman redirector, comes to save us again. And here we can also get some insight into why it shows, why it doesn't track renames. Because multiple UNC provider does not change anything about the file name. Whatever you specify on input, such as double backslash localhost, c:something something, including junction points, it is going to be the same string. You're going to get the same string when you query the name back. So here's the attack vector. We have some junction point. We open a file following this junction point. So using a name that has redirection in it. Then we create an image section, close everything, and then map the section. But wait, before we map the section, we modify the junction point. And the file is still going to report the old name. But now, even though it was the correct name, now it points somewhere else. And if the driver will try to follow it, it's going to end up in a different location where, again, we can plant some other executable for inspection. And I also mentioned, aside from redirection, that there is a potential for ambiguity. And example is transactions. File system transactions work kind of a similar way to database transactions. They allow to group several operations at once and perform them as an atomic action, but there is also isolation, and a file can be in different states visible to the rest of the world and inside of a transaction. And so if we modify a file in a transaction, it effectively is in two states, yet these two states share the name. The name is not enough to resolve the file. Maybe it is inside of a transaction, maybe it is outside. So usually drivers will assume outside of a transaction, of course. But it might backfire because the file have been modified. So it is a technique similar to process doppelganging in action because there is involvement of transactions and different states visible to the rest of the world and the transaction. And then there is an assumption of matching file and memory. Specifically because mapped images are copy on write. They introduce extra level of caching. And I'm not going to go into the details. We still need to cover mitigations. But there are some attacks on this level already known, such as false immutability reported by Gabriel Landau. And also process hyperdereking is a form of this mismatch between the file on disk and whatever gets mapped into memory as an executable. So why did I start exploring this functionality? Well, there was a story with Process Hacker and System Informer. Process Hacker is an open source task manager, very heavily Windows internals oriented. It's like Process Explorer by sysinternals, but open source and more in-depth functionality. It used to have a driver for providing extra capabilities. And even though using this driver required admin, Microsoft and some vendors did not really like it. So there was a bit of bullying happening with the old Process Hacker project. And at some point, there was a rebranding into System Informer, which was taken under the wing of the company owned by Alexei Ionescu. And now the driver of the new System Informer, it respects protected processes for modification requests, but still allows great insight into the functionality. You can see stack traces, handle information, etc., etc. And the goal of the rebranding and the driver-specific part was driver hardening. The idea was to protect the tool from abuse. There are some operations that the driver can perform that normal APIs do not allow. And we want to see them available in the UI. But also, we don't want code to be able to use this functionality for malicious purposes. Usually for these things, you would use something like process protection. However, it's not an anti-malware project, so there is no code signing as a protected process. And also, there needs to be some support for plugins. There are built-in plugins, which are coming from the same maintainers. But there is also some API that allows to create custom plugins. And we want to differentiate between those two to provide different capabilities when there are no unsigned plugins and when there is some external code involved. So we need to reinvent the protection mechanisms based on the driver. And there are a few obvious choices, such as handle filtration for process and thread objects. There is like a two-phase restart that creates it from a clean state. Lots of mitigations. And specifically for plugin differentiation, there is the support with image load notifications. So the idea is the following. I, as an attacker, want to plant an unsigned plugin to be recognized as the official signed plugin, so that the driver does not restrict its functionality. And what worked? Most of the attacks I described. All the name desync attacks that allow you to specify, to make sure the section object returns the incorrect file name. Content desync attacks, and redirections upon the open request. So here's an example of an attack that used to work before we patched it. Let's say we have an unsigned DLL. We use any of the previous methods to create a mismatch on the name. We create a section object, maybe do some renaming or of the object or parent directories, or there are also some hard link options which you will be able to read in the slides, which I cannot cover during the talk. Too much content. And we want this unsigned executable to be cached, to cache the file name of a different file, the file that is digitally signed by the official maintainers. So we have this set up, and before we execute the attack, we do not have code execution in the protected process, protected by the driver means, of course, not Windows protected. So there are some restrictions on what attacks we can use. But if we try to poison the file name, and then we start System Informer, it loads the unsigned DLL, but validates the signature of the wrong file, because it retrieves the file name as a callback parameter, opens this file, checks it for signature. Oh, it is our own file, allow all access. Even though the content in memory, the file that is actually being mapped into memory, is not the same that the file that the driver checked. So that was the attack scenario that worked and that we patched during driver hardening. So when it comes to trying to mitigate this kind of impact, there are a lot of things you need to consider. There are a lot of caveats and difficulties. First of all, always use the extended version of the structure. The regular structure provides you with the file name, the base address, and that's it. The extended version gives you the file object, which is much more compared to just some string. However, it does not solve all of the problems. The issue is that the file object that the image load callback provides is in a cleanup phase, and it is barely usable. You can try to query a name from it, maybe perform some basic operations, but overall, the handle to this file have been already closed, so it is in some limbo state where the object still exists, but it's not immediately usable for all of the things we want to. And Johnny Shaw, the maintainer of the driver hardening in System Informer, and we looked at trying to reopen this file object into the actual file, but unfortunately, we were not successful at it. We wanted to avoid file names altogether, right? If we can reopen the file, we can avoid file name attacks altogether. The problem is, to reopen the file, there is a functionality to perform a relative open operation, and this functionality relies on a file handle. There is no similar functionality exposed based on file objects, and we have a file object pointer which we cannot upgrade because it's in the cleanup phase. It fails somewhere deep in the filter manager stack. So the main takeaway, at least for the fundamental, still try to use the file object as much as possible. When it comes to working with names, since we still cannot avoid it, honestly, we can try harder than the image load callback delivery mechanisms do. Specifically because we saw that the image load callback provides the string as the Unicode string data structure, which has a limited capacity. There is another information class and a function antiquary virtual memory that we can ask about the file name of a mapped executable. And this function does not have a Unicode string limit, so it can return more than these 32,000 characters, which is going to fit the name. And even if it doesn't, even if the file was deleted or destroyed by the volume unmount operation or something else, the function is going to give more insight into what exactly failed. Because if it fails, it's going to return a status code, such as status file deleted, or transaction inactive, or volume unmounted. So useful information. There is also a filter manager function that can return slightly different results compared to the normal name query, because there is some normalization logic and caching involved in the filter manager. So maybe comparing these two can be a way to uncover discrepancies. But the general idea is that you need to explicitly choose what to do with non-existing files. If you get a callback invocation with a deleted file or with a file where the name is messed up, do not try just go and use the default logic of ignoring it, like antiviruses often do. And in case of antiviruses, I guess it's fair. If you see an image load event and the image name is empty, there is no file name, what are you going to do? What are you going to scan, right? There is no file involved. But you usually want to do something, to make an explicit choice at least. If the name is correct, you want to open the file, and there are a bunch of pitfalls here. Such as avoiding access checks. Drivers can easily do that. There are the W and IO functions specifically for kernel callers. There are flags that allow to bypass sharing access checks. There is a way to retrieve the transaction context. So you need to be aware that there are transactions, that if there are transactions associated with the file. There is a flag that allows you to skip the op locking checks. Specifically, you specify this flag, and if the file is locked by an opportunistic lock, the function is going to succeed, but with a special status code that says if you try to do something with this file, you're going to get stuck. So don't do that. But at least you don't immediately just get stuck upon until acknowledgement. If you want to avoid redirections during open operations, there is a useful object attributes flag, don't reparse. Although there are some compatibility concerns here, as we saw, that the file system redirector, the multiple UNC provider, does not immediately discard or resolve all the symbolic links and junction points. So there might be some issues where it breaks things, so beware. And of course, you can also try to compare the object that you opened with the object that you got from the image load callback. That is an essential part of the current protection now. There is a kernel function called nt-rmapped files the same, which is a very descriptive name, and it's a very interesting concept. You give it effectively two files, but slightly indirectly, I will explain in a moment. And it tells you if these two files refer to the same on-disk file, which is very useful, because if they do, you know that you were not redirected upon open operation. Unfortunately, this function is not very convenient to use because it does not receive two file handles or two file objects as parameters. It receives one address of a mapped memory projection as an image and as a data file, which is quite obscure and weird, but if you satisfy these requirements, that is a useful function. If you don't, it does not have a very complex logic. You can try to re-implement it by just copying the same functionality. It accesses some fields in control areas and section pointers. And when it comes to reading content, there is difficulty here. Really, just don't depend on validating the file. What matters is the code in memory. It is the code that gets executed. What happens on disk, sure, it might be useful for static signatures, but this is not exactly the thing that is the crucial here. So validate memory, not file. And if you do want to touch the file, be ready to use the mapped IO because there are some features that allow file read operations to be blocked. I haven't covered it, not enough time, but it is in the slides, and I also wrote a blog post mentioning this technique once. And also, there is a functionality to do image coherency checks. You can find this feature in System Informer. Effectively, what it does is it compares the data on disk and the content in memory. Kind of byte by byte, but with the difference that executable files, they have slightly different layout on disk and in memory. There are some relocations that can be applied. So after accounting for these things, you can compare how well two files match. And if they don't, something is off. You are looking at the wrong file. Or maybe somebody achieved like cache incoherency. So is it a vulnerability, or any of the attacks are vulnerabilities? Well, not really. these are interesting quirks of behavior which you can use to exploit things, probably, with security products. And we saw with System Informer, there are actual issues that were in the driver. However, when it comes to Windows code integrity, the functionality that is responsible for implementing authenticity checks for protected processes and drivers, it does not suffer from any of these problems. It does the things correctly, and we should copy that. We should do like code integrity does, because it validates the memory, not the files. It does open files, but it cares not that much about the actual content. What it wants to see is memory. And it's not too optimistic to grant, say, approve that there is a digital signature, even though there are some potential mismatches. So the takeaway here is it is a very interesting mechanism with lots of caveats and lots of potential attack vectors. And there are more possibilities to uncover. I did most of this research in pretty much a single tool, File Test. It's an amazing tool that covers almost all of the file system APIs that you can invoke. It's a GUI tool for issuing file system API calls. If you want to start, that's the starting point, a great opportunity. And you can immediately try things on Sysmon because it's transparent configurable. I want to thank Johnny Shaw, the maintainer of System Informer's driver and its protections, for the in-depth discussions on the mitigations. And if you want to see more content about the same topic or similar overlapping ideas about file system attacks, I wrote a blog post. There are several blog posts that I mentioned in the slides. Also, the last two links are for similar things, but on Linux and macOS. They also suffer from a lot of difficulties. So thank you for your attention. I have a few minutes for the questions.
Thank you. Thank you very much. Works? Yeah. So we have 3 questions for
Sure.
you. So I will start from the first one, the longer. So is the overflow via long file names an actual overflow from user to kernel land, or is it safe from a memory management perspective and it's more of a functional issue which breaks the file name story mechanism?
As far as I know, it's more of a functional issue. There is no actual buffer overflow appearing. There is the buffer length overflow. So because the system cannot address a string that is too long, it is going to address the overflowed value, which is very short, as we saw on one of the screenshots, where, like, as I said, it looks very cursed. Because the name overflowed to the start and showed only the first several characters, even though the kernel memory has the full strings involved. So as far as I know, there are no actual memory corruption vulnerabilities here.
Okay, thanks. So next one. Are the techniques used to abuse this already detected or easy to detect from a behavioral perspective by EDRs?
That I'm not sure, because a lot of detections from the EDR perspective are quite obscure when it comes to the functionality. Like, it's a black box, right? So you cannot immediately tell what it does and what it doesn't. You need to reverse engineer it. And there are certain opportunities for detection, such as trying to compare different compare information on different levels of abstraction, right? We saw some indirection involved, and within this indirection, you can try to query from multiple different sources or using multiple different ways. And if you see a mismatch, you know something is wrong. Or maybe it's another quirk of Windows functionality, who knows? So I'm not sure about the actual examples of detection for these things, but certainly possible, and yeah, that's just weird quirks of functionality.
Thanks. And last one, how feasible is a scenario where you don't have admin permissions? Is it necessary for the virus to have at least local admin permissions?
So none of the attacks that I mentioned require admin permissions. All of them are low privilege attacks, maybe not as low as like a sandbox subcontainer type of functionality, but things like deleting files, working with renaming, creating image sections, none of these things require admin permissions. So these are low privilege attacks. Even though we are attacking a driver, we are not violating security boundaries here. So it's not that important in this use case, but I do prefer low privilege attacks, and there is a huge attack surface available when it comes to manipulation on the file system level.
Thank you. Thank you, Denis. Thank you, Denis.
Thank you.